This video covers the uniform prisms and antiprisms. A uniform polyhedron has regular faces and identical vertices. This includes all the convex semi-regular polyhedra, such as the Archimedean solids, but also allows non-convex polyhedra. The convex prisms and antiprisms were covered in an earlier video, so this time we'll focus on the non-convex ones. A prism is two identical faces separated by a band of squares. The convex prisms are simple objects with a flat appearance, but non-convex prisms allow a greater variety of shapes. Among the simplest are the pentagrammic prism, the 702 gonal prism, and the octagrammic prism. They get rounder and flatter as the number of sides increases, but only if the density remains low. If the density is also high, they appear more jagged, like the 57/14 gonal prism, or this exceptionally spiky 57/28 gonal prism. An antiprism is two identical faces separated by a band of triangles. Convex antiprisms are relatively simple shapes, like their equivalent prisms, but non-convex antiprisms can become a lot more complicated, as the triangles intersect each other many times. This is particularly true if the density is high. This exquisite figure is a 79/38 gonal antiprism. It has 160 faces, but the huge number of intersections between faces divide the outer surface into 11,398 facets. There is another type of antiprism which has no convex equivalent. Imagine assembling a simple hexagonal antiprism. Put a hexagon flat on the table and fix triangles to the sides. The top doesn't quite fit, but if we angle the sides outwards slightly, it goes into position, its vertices joining to the tops of the triangles. We just have to add the top triangles and we have an antiprism. Similarly, starting with a pentagram, add the lower triangles, angle outwards, then add the top and upper triangles. However, with the pentagram, there is another way to get an antiprism. Instead of angling the triangles outwards, angle them inwards. The top pentagram fits on top, and we get a different type of antiprism, called a crossed antiprism. Crossed antiprisms are flatter and more complicated than their standard counterparts. They don't exist for all possible end faces. You can't make a 7/2 gonal antiprism because the triangles won't lean inwards far enough. They can only exist if the density is more than 1/3 of the number of sides, so a 7/3 gonal crossed antiprism does exist. The next is the 8/3 gonal antiprism, then 9/4 gonal, and so on without limit. The triangle is a boundary case. Its density, 1, is exactly 1/3 of the number of sides, so you can make a triangular crossed antiprism, but the sides have to lie completely flat to reach the other side. This is one of the weirder degenerate polyhedra, 8 coinciding triangles. Crossed antiprisms are strange objects. The triangles pass right through the object and out the other side, so both sides of each triangle are exposed. The figure as a whole has no well-defined inside surface and outside surface. It does have two surfaces, so it's not like a Mobius strip or Klein bottle, but each surface is partly inside and partly outside. If we chop off a vertex and look at the vertex figure, we can see why. The crossed antiprism's vertex figure is a crossed quadrilateral. Two of the triangles meeting at each vertex intersect each other. The three triangles go around the vertex one way, but the pentagram goes the other way, so the pentagram is actually facing inwards. A retrograde 5/2 gon is sometimes called a 5/3 gon, so the 5/2 gonal crossed antiprism can be seen as a 5/3 gonal antiprism. To close, here are some images of the more exotic antiprisms.